Okay. So this section 5 is called electrical principles. It's kind of from the basic stuff. A lot about reactance, impedance, get a little bit into impedance matching and Q. So some of the questions that are going to be on the exam are things like what is reactance, what unit do you use, what's the letter to represent it, what causes the opposition to the flow of alternating current in an inductor or capacitor, how does an inductor react to AC, and how does a capacitor react to AC. We'll talk about that. So on this one, yes. Reactance is defined as the opposition to AC current flow in an inductor or capacitor. Those are frequency-dependent elements, where resistors are not frequency-dependent, unless, of course, it's a wire-wound resistor. And there's a question about that. We measure reactance in ohms, just like we do resistance. We use the letter X to represent reactance, and inductive reactance for an inductor is 2 pi times the frequency times the inductance. That gives you the reactance value in ohms. For a capacitor, it's 1 over 2 pi times the frequency times the capacitance, so it's a reciprocal. As you see on the next chart, because of the 1 over, the capacitive reactance is not linear, where inductive is. The key point is where they cross. When the inductive and capacitive reactances are equal, it's where we have resonance, and it's purely resistive in an LC circuit. If it's series, it's going to be equal to whatever the resistance is in that circuit. If it's parallel, it's going to be equal to the resistance in the circuit. At low frequencies, a series circuit will have high impedance. At high frequencies, a series circuit will have high impedance. At resonance, it will be, if it was no resistance in the circuit, it would be 0. But there's always going to be some components.
Excuse me, are you sharing the correct screen? We're having all we can see is the list of files.
Oh, sorry.
Thank you.
Why? It says it's sharing.
You're not sharing the right thing.
Hmm?
You're not sharing the right screen, is it?
All right.
It's the one to the left.
You see it now?
We now see LibreOffice, yes.
Okay. Let's.
Thank you.
Oh, okay. I copied this chart from somewhere, and they made a mistake. And one of the things that you see is at low frequencies, this circuit is going to appear to be capacitive. Above resonance, it becomes inductive. That's important because it determines how a lot of things in radios work, but it's also a question on the exam. The main thing is for resonance, capacitive and inductive reactances are equal. So they basically cancel out. That's why you just have the resistive term. So the question is, what is reactance? Ed?
Looks like B.
Everybody go with B? Bravo sounds good.
We're all wrong.
What unit is used?
Mr. Ohm.
Mr. Ohm. Okay. What letter is used?
X-ray.
X-ray. Which of the following causes opposition to the flow of alternating current in an inductor?
Reluctance.
Huh?
Reluctance is cute. Yeah.
Delta.
I heard a delta.
Yeah.
Which of the following causes opposition to the flow of alternating current in an inductor? Well, they do that because you only get one of these questions, so it's either the inductor or the capacitor. So we'll go with delta.
Yep.
Which of the following? Oh, we did that. How does an inductor react to alternating current? So you can throw 2 away because you know it doesn't have anything to do with amplitude. So you got a 50-50 chance. Ron?
D. Ooh.
You get that one?
Do it now.
It's frequency dependent. Okay. Inductors oppose at high frequency. Capacitors oppose at low frequency.
Well, what's considered low and high in that case?
Well, low frequency would be 0 or DC.
Right.
An inductor at DC has only its internal resistance. At an infinite frequency, it has an infinite reactance. Where a capacitor is just the opposite. You have to get up to extremely high frequencies before it has low reactance, and it's limited by whatever the internal resistances are. Called the ESR, the effective series resistance. Okay, so we talked about reactance. Now we'll talk about impedance. Reactance is part of impedance. And impedance is the resistance of a device or circuit when alternating current is applied, because it becomes a complex value. We're going to get to some imaginary stuff. And we're talking about what term is used, what happens. And we talked about the reactances being equal in series and parallel circuits and resonance. So, and a little bit about impedance matching. So impedance is the vector sum of the resistive and reactive opposition to AC current flow. We measure it in ohms. We use the letter Z for impedance. And the impedance is equal to the resistive or real component plus the imaginary reactive component. And if you're not familiar with J, everybody know what J represents? Ed?
Wow.
You know what J represents? Yeah.
Yeah.
Well, in mathematics, they use I for the square root of -1.
Right.
And for some reason, in electronics or electrical engineering, they use I for current. I never figured out that relationship, but I was already taken, so we use J.
Oh.
So J is the square root of -1. And it's in the complex plane because you have a 90-degree phase shift with reactance, either positive or negative. And that's why you write it that way.
And there is no such thing as the square root of -1.
Sure there is. It's J.
Well, -1 times -1 is 1. That's what the
Right.
imaginary number, right? Yeah.
So it's the square root.
Yeah.
And the impedance is the ratio of the voltage to the current in magnitude. Then they throw in a little bit about, we got a Harold up there. Throw in admittance, which sometimes it's easier to do things in the admittance world as opposed to impedance world. Admittance is the reciprocal of impedance. So it's just 1 over Z. And it uses terms like conductance and susceptance instead of resistance and reactance. G represents conductance, which is the reciprocal of the resistance. So it's how well it conducts as opposed to how well it resists. And B represents susceptance. I don't get that connection either, which is kind of hard to explain, but it's the inverse of reactance, whatever you would call that. And remember that G is used to represent conductance, B for susceptance, and Y for admittance. If we plot impedance, okay, we plot the resistive part or real part on the real axis. We plot the reactance on the imaginary axis. If it's inductive, it's positive. It'll be a plus J. If it's capacitive, it'll be a minus J. So if you've got both in the circuit, it's the net result of the positive and negative. So you'll either be a plus or a minus J.
Okay. Okay. I can't believe this shit.
Did you say something? The impedance is the vector, okay? So it's, if Pythagorean's theorem, it's the square root of the sum of the squares of the two sides of the real and the reactive part will give you the magnitude of the impedance. The angle, so phase angle that's associated with that is going to be the arctangent of the reactance divided by the resistance. So a lot of times you'll have an impedance magnitude at a certain phase angle. And that's where that comes in. You do that with power factors, which we'll talk about later. So what is impedance? Out of those four choices. Any guesses?
B. Delta. Oh.
It's just like resistance. Voltage to current.
When you play with big amplifiers, you'll remember.
Huh?
When you play with big amplifiers, you'll remember.
So what is the term for the inverse of impedance? Whereas impedance impedes, so what is the opposite? Admittance, it admits. Okay, impedance matching. We can use, well, the intent is to get maximum power transfer between your transmitter and your antenna in most cases. There's three common techniques. You use a transformer, either Balun or unun, where the turns ratio will determine, the square of the turns ratio will determine the impedance ratio for matching. So if you have a 7-to-1 turns on your toroid or transformer, you're going to have 49-to-1 impedance ratio. You can also use an LC network. A pi or a T are very common, which you used to see on tube transmitters, usually followed by a pi or a T network. Or the antenna tuner would have that in it if you got an external one. I still don't know why they're still calling them tuners, because it's impedance matching. Or you can use a quarter wave transmission line stuff, because at a quarter wave, you get essentially the inverse of whatever you put in. So if one end of a quarter wave is shorted, it's a high impedance at the other end of it, because it's that quarter of a cycle. Okay, so sometimes they use resonant circuits to do impedance matching. And in that case, you have to consider what the bandwidth is for if you're trying to match a wide range or a narrow one. And it's going to determine what the Q of the components are. The higher the Q, or quality factor, which is a representative of how closely it resembles an ideal component, like a perfect inductor or a perfect capacitor would have infinite Q. That's not real world. The higher the Q, the narrower the bandwidth for that circuit. And you see on some of the plots how sharp some of those curves are. So if you need to cover match a fairly wide bandwidth, you need to have lower Q components. This chart just shows the difference between your source and load, where your maximum efficiency is when they're equal. So if I have 50 ohm source and I have a 50 ohm load, I'm going to get maximum power transfer, which is only 50%. I mean, the best you can do is 50%.
Where does the other 50% go then?
Well, half of it went in your transmitter.
Reflected back? Or?
No, that you lost in your source impedance.
Oh.
And hopefully the other half gets radiated by radiation resistance in the antenna. Of course, real coax has some loss, so you're going to lose some along the way also. But theoretically, the best you can do is 50% of the power to the antenna.
That messed me up. Well, look, if you have a 100-watt transmitter, and
you're putting out 100 watts.
It's putting out 100 watts.
Okay. And
you've got a perfectly matched antenna.
50 ohm antenna.
50 ohm antenna.
Right. Got ultra, your LMR 600 or something in between.
LMR 1 million. You're only going to get 50 watts at the antenna.
Essentially.
Mm-hmm. What?
I know, but it's law of physics.
Now, where's that other 50 watts again? You're starting out with 50 heat.
If you look at your transmitter, your 100-watt transmitter, you see a heat sink, don't you?
Yeah.
What do you think that's for?
You know, 50 watts. So if you get rid of that heat sink.
Yeah. And, feel it and see. It's warm. That's why the modern ones also have temperature regulators, and they start shutting power down as temperature goes up. Because in semiconductors, which we'll talk about next week, you have the problem of thermal runaway. As silicon gets hot, its resistance goes down. So you have to compensate for that in a transistor amplifier.
So how does this affect the way you operate when you're looking at your chart to see what your limits are? Some bands are PEP and other bands are VRP.
Well, you're assuming that you're going from your loss in the transmitter out to the receiver. So if you're measuring that power, that's the power going out. I'm not sure how to answer that.
Can I ask a question related to that?
Okay.
So let's say if you take that 100-watt transmitter that's supposedly putting out 100 watts of RF power, again, going through a perfectly matched coax line, straight into a pure resistive dummy load that's going to be matched. The thermal measurement you make at that dummy load is how you can calculate transfer of energy, correct? You can calculate the temperature rise, knowing the mass, and calculate how much energy it takes to raise that. Would you see at that point with a pure resistive element as a load, where we're not radiating it and having to capture the RF, but just a pure resistive, turning it into heat that we can measure, are we going to measure 50 watts of thermal power being transmitted or dissipated by that dummy load, or are we going to measure 100 watts of thermal power?
Well, I guess I was slightly misleading. You do lose 50%, but that means if your transmitter is actually rated at outputting 100 watts, that means the input is more than 100 watts to get 100 watts out, because you're going to lose 50% of the power.
So effectively, the amplifier circuitry, chips, et cetera, in the unit, in the transmitter, are basically overrated, or not overrated, but basically they're underrated as to their listed capabilities, so that they will produce the desired RF output, and that's the way that they're listed and or rated at that point, right?
Right. They have to correct for the inefficiency, and because you're going to lose that power, so you've got to have, if you want 100 watts out, you're going to need more than 100 in. I mean, if you look at like a typical 7300, to put 100 watts out, you need 22 amps at 13.8 volts. Well, just figure out the wattage. It's a lot more than 100 watts.
Okay.
But that prime power, that prime power rating is for the whole radio, not just the power amplifier.
Well, true, but usually the other parts of it, when you're not transmitting, you're only going to draw 1 or 2 amps.
That difference would be the RF portion of it. Okay. All I was saying is that the total current from the 13.8 is not the final amplifier.
But if you look at the difference between transmitting and not transmitting, that delta current times the voltage is going to be a lot more than 100 watts.
Of course.
Okay. Which of the following devices can be used for impedance matching at radio frequencies?
What's your favorite answer?
Delta.
Finally got a delta. All these are correct. Okay, resonance. We talked about a little bit. So we'll talk about RLC circuits, how the magnitude of the impedance changes, the magnitude of the current and the voltage. You've got some circulating currents within them. So the formula for resonant frequency is 1 over 2 pi times the square root of the inductance times the capacitance. You can derive that by setting the inductive reactance equal to the capacitive reactance. You do a little algebra and you come out with F's equal to 1 over 2 pi square root LC.
Are you missing the slash in that last formula? 1 over parentheses 2?
Yes,
Yeah.
You're right. I missed that. So if you can't remember that formula, just remember the two reactances, and it's fairly simple algebra. If you remember algebra.
It was only 100 years ago.
So here's an example of one of the kinds of questions. What's the resonant frequency of an RLC circuit where R is 50 ohms, L is 40 microhenries, and C is 50 picofarads? So I just plug those into the formula with my calculator, and this is one of the questions that you probably need a calculator to do, unless you're a good guesser or can round off. A lot of times you can do it in your head. And it comes out to 3.558 megahertz.
So it doesn't really use the ohms, the resistance.
Right, that's just a red herring.
All right, I can't do it in my head.
Okay,
But resistance is ohms.
right.
Capacitance.
Resistance does not affect.
No, I'm sorry. Inductance is farad, or is henries, right? And capacitance is farads. And the resultant frequency would be hertz?
Yes,
Okay.
and depending on where the decimal point is, megahertz or.
So what you did there is you took the exponents and
Right,
and maneuvered them around, and that came up to 3.55.
right. Because see, you got a 10 to the minus 6 and 10 to the minus 12 multiplied, so you got a 10 to the minus 18. And you're taking the square root of it, so it'd be 10 to the minus 9 times whatever that is.
Yeah, it's square root of 10 to the minus 9.
If you do it on the calculator, that's the number you'll get. And those are some of the ones that you should practice, because it's easy to make a mistake doing those. And most people can't do that in their head.
Well, the calculator will come out to 3 million.
It might, or it might be in scientific notation.
Yeah.
Depends on the calculator and mode.
Keep it back for just 1 second.
Okay.
That's good. So if the resistance was infinity, the frequency would be the same? Or is it? Or
Yes.
Say at radio frequency.
Although you couldn't see much if it was infinite, unless it was a parallel circuit.
Well, that's a different formula, right?
But if it's a series circuit, then obviously you never get any current through it. And it requires a little bit of current in order to have resonance, because resonance is just the energy that gets stored in the magnetic field and the capacitive field. So it goes back and forth from electromagnetic energy to electrostatic energy, because you got an H field in one and an E field in the other, and you're just moving the energy back and forth between them, and it's equal.
And that gives you that rate of change is the frequency.
And that current that's going back and forth is lockless power, because there's no power dissipated unless there's series resistance in it. Does that make sense? Okay. So let's do a real one. We got 22 ohms, which you can forget. 50 microhenries and 40 picofarads. So, Anybody got your calculator? And I forgot mine. So we got another 10 to the minus 6 and 10 to the minus 12. And 50 times 40. This is one of those where it's not intuitively obvious, which are the ones you can throw away. Unless you've done these before. Any clues? Yeah, it's the same.
Didn't know it's close to the last one, I can guess. Let's see.
We're gonna go with Charlie.
Yeah.
Okay.
Calculated.
Yeah, it was the same as the example, except for the resistance.
We always like to throw. I always like to throw a little. Think about it in there.
Okay, now this one's different. It's 50 and 10. So in the last one, we had 2,000 times 10 to the minus 18. Just take the square root of it. In this case, we got 500 times 10 to the minus 18 square root. So you can kind of guess at that ratio. Oh yeah, there's tricky there too. They got kilohertz.
Yeah, that's one of those left field answers.
So it's basically twice because it was a ratio of 4. Take the square root of that.
And we haven't mentioned pi,
Oh, okay.
but it's in there.
Yes,
Yeah.
pi is very important. 3.14159. Right. All this stuff turns out to be based on pi. because there's most of the formulas that we see here, you use 2 pi f. In engineering, you learn that that's omega, which is 2 pi f, which is the radiant velocity. So the way all this stuff is derived, if you think of a circle, it has a radius. So regardless of what size the circle is, the radius is 1 over 2 pi of the diameter of the circumference. So we call the radius a radian. So regardless of the size, 1 radian is 1 over 2 pi of the circumference. You can generate a sine wave by rotating that circle and measuring the height. In other words, you do the sine for every degree, you go all the way around. It's like, think of somebody riding a bicycle and you're watching their foot on the pedal, it makes a sine wave as they travel. Same thing. That's how a lot of this stuff is actually generated. And it's easier to use omega than writing out 2 pi f most of the time. So that's the way I learned it.
But wouldn't that confuse you with ohms? Omega is a symbol for ohms.
No, it's a little omega. Looks like a W.
Oh.
There's a difference between uppercase and lowercase Greek letters.
No, that's awkward.
So, but yeah, you're going to see pi pop up all the time. In other words, it was in your reactance formulas. So let's talk about a series RLC circuit. So the impedance is going to be the real part, or resistance, plus the inductive reactance minus the capacitive reactance. So if you have an L and a C, you add the reactances where capacitive is negative, and the result is going to give you R plus or minus J, depending on what it is. So for a frequency of near 0 in a series circuit, you're going to get whatever the resistance value is, and you're going to get a minus J infinity, because it's going to appear capacitive.
So on the previous one, where they were all parallel, the resistance, conductive, and capacitance were all strictly in parallel.
Okay.
That was a question I was making.
It doesn't matter as far as resonance.
Because normally it's your inductor goes to the output and your capacitance goes back, is what I think of an RC circuit.
Well, in a resonance circuit, it's either inductor and capacitor in series or in parallel.
Oh, the components are in parallel.
Yeah. And typically you see the parallel one called a tank circuit, because it's storing energy back and
Charging back. Yeah.
So for the series circuit, at low frequency, it appears capacitive because your inductor is not having any effect. At DC, the inductor has no inductance, but the capacitive has maximum reactance. So it appears capacitive, so that's why you've got a minus J. If you go to a high frequency, where you're approaching infinity, it's just the opposite, because the inductor is the large component, and the capacitor has essentially 0 reactance. So you're going to get a positive J. So it'll appear inductive. At the resonant point, they cancel out, and you get whatever the resistance, the series resistance is. whether it's a resistor in series or the series resistance of the inductor and or capacitor.
Does it matter which way the components are arranged in the
No.
series circuit?
LC or CL? No.
Yeah.
Put R in the middle, that doesn't matter. Because the current through them is the same, regardless of their position.
What's the last dot there? I equals E over R equals everything greater than zero. What's that symbol indicate?
The current is equal to E divided by R, so it's going to be much, much greater than zero.
It's going to be what?
Much greater than zero, and it's going to appear resistive. Because in a series circuit, remember, it's high impedance and essentially zero impedance at resonance. So that's where you get maximum current, is at resonance. It's limited by the series resistance. So it'll never be less impedance than whatever the resistance is. And there's a circuit with some components.
Yeah. I wish you showed that earlier.
Yeah.
Would make more sense.
I'll fix that. I plotted that in a thing called Circuit Lab. So you can see how the impedance varies with frequency. And we get down to 1 ohm because it was a 1 ohm resistor in series. So that's the lowest it can be. And then it starts going back up. Below is the phase, and you can see we have a phase shift, and at resonance, the phase is zero because it's purely resistive. There's no reactive inductance or capacitance. If we look at the voltage, okay, because the impedance is dropping, the voltage goes to a null. The current goes to a maximum, limited by the resistance.
Can you go back 2 slides, please, to that impedance graph?
Okay, I'm getting a double click here. Previous one?
Yes, sir, please. That one right there, the vertical scale on the slide, the way it's presented, the vertical axis label on the left is cut off just a little bit. What is the vertical text that's to the left of the numbers 40 and 60? The vertical scale
dB.
label. dB? Okay.
dB ohms.
And you use dB because the logarithmic scale of a dB with respect to an ohm gives you the linear chart as it goes left and goes right upwards away from 1 ohm in the middle of that graph. Is that correct? Otherwise, it would be an exponential curve because of the squares.
Right.
Okay.
It just lets you show it on the graph a little bit better. The point there really is the fact that it goes to the minimum, to whatever the resistance in the circuit is.
Okay.
And you can
And
see
so then everything else with respect to that, the vertical scale is all just measured in dBs with respect to the ohm that you get at the center of that.
dB relative to 1 ohm.
Okay. All right. Thank you.
And you can see at 1 hertz, we're over 100 dB, which is a lot. It's a lot of ohms.
Well, a lot of ohms. dB relative to what then?
Huh?
Is it dB relative to 1 ohm? Is that the rate? Is that the scale?
Right. You can have dBs relative to anything you want.
Well, it's a unitless measurement. So.
Okay, so what happens when inductive capacitive reactances are equal in a series LC circuit? Got a guess?
Delta. I think it's delta.
Charlie.
It's delta?
Either bigger or delta.
Come on, Ed.
Well, oh, come on.
What were we just talking about?
I don't know. Oh, that's the,
Right. I went to all the trouble to make that chart. You understand it now? You'll probably get another chance here. What's the magnitude of the impedance of a series RLC circuit at resonance? I told you the answer to this one.
Delta.
Delta?
yeah.
Very good.
This is going to be
What can cause the voltage across the reactances in a series RLC circuit to be higher than the voltage applied to the entire circuit?
Alpha.
I think I heard alpha online. Oh. Resonance is what we've been talking about. That's not exactly how it works, but resonance can cause higher voltages across the components in a series circuit. The current has to be the same, but the voltages can vary. And they actually vary based on the Q. So the higher the Q, the higher the voltages can be. If you had a Q of 2, and we were applying whatever voltage that was, say it was 10 volts, you'd see 20 volt peaks on those components between them. In a parallel circuit, you get just the opposite. The voltage is constant, so the current can be different between the inductor and the capacitor. What's the phase relationship between the current through and the voltage across a series resonant circuit at resonance? Remember I showed the phase plot?
Yep.
What happened to resonance?
C.
In phase. Okay, a parallel RLC circuit. The math's a little more complicated because now we're doing, if you remember how to do parallel resistors or parallel inductors, where you have to do the reciprocal of the sum of the reciprocals when you got more than 2. That's the way you have to figure out impedance in a parallel circuit. The bottom line is you get just the opposite behavior. It appears inductive at low frequencies. It appears capacitive at high frequencies. And of course, it's equal to circuit resistance at resonance. So we take our typical circuit with a 1 microfarad and 1 microhenry and a 1 ohm resistor, and I didn't label what the voltage was, but it doesn't matter. So you're going to see an impedance plot where it's going to be basically 0. Well, actually, it's going to be 1 ohm. And go up to this hot to a peak at resonance. You're going to see the current dropping. It's going to behave just the opposite of a series circuit, where a series circuit goes low at resonance, parallel circuit goes high at resonance. what's the magnitude of the impedance of a parallel RLC circuit at resonance? So remember, we're thinking of parallel resistances or reactances, impedances, I should say. So we're going to have a very high impedance in the LC in parallel with a resistor. So what's the result?
It's gonna be high. Double that.
Alpha.
We got two impedances in parallel. One's high, one's what, 1 ohm? Or whatever it was.
The resistance.
So it's going to be equal to resistor. If you didn't have a parallel resistor, then it would be on its way to infinity. And down there's how you figure that out.
How do you do it?
Well, it's the reciprocal of the sum of the reciprocals. What's the magnitude of the current at the input of a parallel RLC circuit at resonance? Remember the graph? What happened with current?
Minimum.
Minimum curve, maximum.
Minimum. Just the opposite of series. Okay, talk about phase. And what it is and what the relationship is between current and voltage on series resonant circuit. Similar effect on parallel. I tried to come up with a good definition, but phase is just a representation of what fraction of an AC cycle waveform. So you have, remember I talked about radians, you have 2 pi radians in a complete cycle. Or 360 degrees, depending whether you want to do degrees or you want to do radians. So a 90-degree phase shift is also represented as pi over 2 radians. And you'll see that a lot when we talk about wavelengths and things, or like quarter wave stubs. So as you go through the cycle, okay, you get a max for a sine wave, you get a maximum at 90 degrees, it's back to 0 at 180, you get a negative maximum at 270, and back to 0 at 360. When you have inductive or capacitive components, okay, the current and the voltage get out of phase. Where in a resistor, the current goes up when the voltage goes up and down when it goes down. In the case of an inductor, we'll do Eli. Thing to remember is Eli the Iceman. Never heard Eli the Iceman? Great way to remember it. It says the voltage, E, in an inductor, L, leads the current, I. The current in a capacitor leads the voltage, E. So it's a simple way to remember how the two work. So in an inductor, the voltage leads the current because you get a lag in current flow through an inductor. You have to apply a voltage and you're up to 90 degrees phase before you start seeing current flow because of the 90-degree phase shift between voltage and current. So the voltage, we say it leads because the voltage goes up before the current goes up. In the case of a capacitor, it's just the opposite. The current goes up because you've got a discharged capacitor, you put a voltage on it, and what happens? You get an infinite current for an instant. So Eli the Iceman is the easy way to remember those. And this one is showing the phase shift, where again, at resonance, phase shift is 0. This is showing Eli, voltage leading the current. This is Iceman, current's leading the voltage. So what's the phase relationship between the current through and the voltage across a series resonant circuit at resonance? All right.
What resonance means.
What's the magnitude of the circulating current within the components of a parallel LC circuit at resonance?
Maximum.
I heard of Bravo. Got a wild guess or a smart guess?
Probably.
Maximum. I mean,
This all comes back to memory from tuning two type radios.
yeah. It's the same physics. In the parallel circuit, you've got a constant voltage across all the components. So the only thing that can change is current. In series, you got a constant, I shouldn't say constant, you got the same current flowing through all the components. So the voltage across the L and the C can vary. So if you had, say, 10 volts in, and you had 20 volts across the inductor, you could have a minus 10 volts on the capacitor, okay, to equal the 10 in. So you can see that much bigger. It's like a standing wave that you might see on reflection from your antenna. So what is Q? We've talked about it. And how do you calculate it for a parallel, or we'll talk about in a series circuit, and what effect is it? So it's called quality factor. Like I said, it's a measure of how close to an ideal component the inductor or capacitor is. It's also a measure of the energy stored versus the energy dissipated. In the case of a parallel circuit, and these were hard for me to remember, okay, you calculate Q by dividing the series resistance by the reactance of either the inductor or capacitor, because at resonance, where you figure the Q, they're equal anyway. It doesn't matter which one you use. In a series circuit, you obviously do the opposite. You take the reactance and divide it by the resistance. That one always kind of bothered me. But I think the question on the exam is about parallel. But main thing is they're just like most things in the series and parallel, they work opposite. So in a parallel circuit, you've got a parallel R. So the higher that parallel resistance is, the higher your Q can be. Because if you have a low reactance and you divide R by a large R by a small reactance, you get a high Q. The smaller that resistance is, it lowers the Q of the circuit. So that's one way to kind of change the Q by whatever that parallel resistance is. In series, you're for high Q, you want a low series resistance.
Could you say that the Q in a parallel circuit is just the resistance divided by the reactance? Because it's resonance, so the capacitive and the inductive reactances are the same, so just say reactance.
Okay.
Take that confusing L and C out.
Okay. You're right, if that's the way you want to think about it. It doesn't matter which one you use, it's just what you have to pick one.
And at resonance, it's the same.
Right. But you have to know what it is. You have to have its value.
But that's where you toss a coin.
Well, you have to calculate one or the other. 2 pi FL or 1 over 2 pi FC. Or in engineering terms, omega L or 1 over omega C. That's always easier. But I don't want to confuse you anymore.
Well, you blew that up.
Here we have a parallel RLC circuit, and I think what they're doing in this one is a bunch of calculations on it. They calculated the resonant frequency with our 1 over 2 pi times the square root of LC formula. For some reason, whoever did this uses these dots as multiplication signs as well as decimal points, so it makes it very confusing. So it's supposed to be 0.2 times 120 times 10 to the minus 6.
God,
I don't know. I didn't do it, I just copied it. I might do it over myself. It is very confusing. And then they calculated the inductive reactance, okay, 2 pi FL. So it's 2 pi times 32.5, which was the frequency. Okay, so 2 pi F times L, and L is 0.2 henries. Okay, 200 millihenries is 0.2 henries. And it came out with 40.8 ohms. They calculate the Q. Get that out of the way. By dividing resistance by the reactance. So we knew the reactance was 40.8 ohms. And the resistance is 60. So you get a Q of 1.47. The bandwidth then is going to be the frequency, the resonant frequency divided by the Q. So in this case, 32.5 hertz divided by 1.47. So the bandwidth is 22 hertz. It's fairly wide bandwidth for that frequency, but it's very low Q.
So if we want to make the Q sharper, what we would have to do is, and we can't change the resistance.
Yeah, you could.
Well, I'm saying we cannot change the resistance.
But you can also pick your L and C values for the reactance you want at resonance.
And you want the reactance to be higher? or a sharper Q?
No, you want it, in this case, you want it to be lower.
Because it's R over the reactance.
So you can put a larger parallel resistor, so you put a 1K there, and we divided it by 40.8, so it's going to be what, Q is 25 or whatever, so much higher Q. But your bandwidth would really go down.
So the larger, sharper.
Right.
Small questions. In this parallel circuit, you show the resistance in parallel. The previous one is kind of in series before the two were in parallel. Does that matter? I mean, I think there's a big difference if you put the resistor in series versus in true and parallel.
Well, in a series RLC circuit, you do the Q just the opposite. In other words, you do R divided by,
okay,
reactance divided by R.
I'm sorry, my question is how you're doing the circuit, not the math.
Okay.
So you see how all your resistance, conductor, and capacitor are
parallel. It's a truly parallel circuit.
In your previous one, the resistor was not in parallel; it was feeding into the two parallel elements instead.
Oh, it was?
Yeah. You don't need to go back. It's just
well,
that would make a huge difference.
I think.
I don't know.
Yeah, I think I know what you're talking about. I did that in the circuit model to be able to have a way to measure.
Right.
Way back there.
And then was way back there when you were.
Yeah. But yeah, I did that on purpose for the circuit simulation to be able to measure the current.
But where you put that on resistor changes a lot of things.
It doesn't change the Q of the circuit, though. I don't think.
Well, the Q is determined by the capacitor and inductor, not the resistor.
No, it's got the resistance.
Well, it's got the resistance of the LC circuit, RLC circuit.
But does it make any difference if that resistor is in parallel with the capacitor and inductor, or if it's in series?
It would, because the voltage at those two parallel components is going to be different than if it was in parallel.
Right.
So it matters quite a lot, I think.
Well, if it's in parallel, the maximum resistance of this parallel circuit is going to be whatever that resistor is. It's going to be that or less. Because it starts essentially at zero, because your inductor is a short circuit at zero. If you had it in series, then you've got whatever that resistance is and a varying reactance that's going to be anywhere from 0 to infinity. So yeah, it would have a different effect. I'm not sure how you would calculate it, but you don't have to calculate that one.
Sorry, I didn't mean to go off topic.
That's okay. So, all right, we did this nasty one. This is a similar circuit series. You're doing the same calculations and doing the Q where you're dividing the reactance of one of the components by the resistance. In this case, we had a 30 ohm series resistor, and our reactance was 100. So you're getting a Q of 3.3, and you can see you have a wider bandwidth. Well, I shouldn't say wider, but out of 800, you got a little over 200, so up 1/4.
What does it mean by bandwidth years?
The frequency between the lower cutoff and the upper cutoff, which is 3 dB half power points,
okay,
which is probably the next chart, or one after.
Okay.
So the higher the Q, okay, the more the circuit behaves like ideal components, and obviously the less resistive losses you have, but you get much higher internal currents or voltages depending on whether it's a series or parallel circuit. So in the case of a transmitter with a tank circuit, if it was very high Q, you look at a fairly narrow band, you could get some very high voltages on that thing. So what's the result of increasing the Q of an impedance matching circuit? So we're going to use one of these RLCs or Pi's or T's.
Alpha.
Right. How's the Q of an RLC parallel resonant circuit calculated?
Yes.
See,
Charlie? Charlie. What's an effect of increasing the Q in a series resonant circuit? We talked about this a little while ago.
Charlie, definitely.
Because you know you can't, the current's the same in all of them, so. The voltage increase based in, I don't know that we get to it, but multiplied by the Q. So bandwidth, when we talk about the half power bandwidth of a resonant circuit, and we just did the increasing Q of impedance matching. So the half power bandwidth is a function of Q. It's where in a series circuit, it's the bandwidth that will pass half the power of the input signal. In a parallel, it's the bandwidth that will oppose or reject half the power of the input signal. And the formula is the 3 dB down bandwidth is the frequency divided by the Q, which we just did before. So increasing Q decreases the bandwidth. So what's the half power bandwidth of a resonant circuit that has a resonant frequency of 7.1 megahertz and a Q of 150? You do that in your head.
just knew what the numbers of the code were.
So what's the formula? Frequency divided by Q. So 7.1 million divided by 150. A little less than 50 times, right?
Mm-hmm.
You look puzzled.
Oh, I'm always looking.
Rusty.
Well, I want to make sure you understand this,
Well, I'm working.
because one of my goals is for everybody to pass. I'd be very disappointed if you don't. What's the half power bandwidth of a circuit that has C of 3.7 and a Q of 118. See if Kelly's been paying attention.
Oh, I haven't, but I can tell you all about vaping if you're interested.
What day is this again? In the twilight zone.
Oh. Okay, I got it.
You got it?
I do.
What is it?
I'm not sure. I'm not sure, but I think.
Think of Charlie. Well, let's see. Yep. Charlie, very good. Get a star. Okay, so we talked about impedance being the vector sum of the resistance reactance, and it's the ratio of voltage to the magnitude of voltage to current. Admittance is reciprocal of impedance. You don't use that much, they just throw those in there to kind of confuse you. I can't remember actually ever using admittance, except in school. Impedance matching is where you're going to try to match the source impedance to the load impedance, which is what an antenna tuner does with some intermediate circuit that's trying to compensate. Either they're doing it with a pi or T network. If you do it with a transformer, you're using the turns ratio to give you the impedance ratio you want, or transmission line stubs, which sometimes you can use.
Which one's the most efficient of those?
Hmm?
Which one of those is the most efficient way of doing things? Yes, that's the one.
It really depends on what you're trying to match.
Mm-hmm.
If you, let's see. The one they don't mention, well, actually, if you've got a dipole high enough up where you might be getting it up to 100 ohms, it's normally 72, depends on height and various things, and you're trying to match it to 50, you could stick a quarter wavelength of 75 ohm in series, which would match 100 to 50.
But you'd be stuck at that one frequency then, right?
Yeah, for that particular bandwidth. You could do that with because it's only a 2-to-1, it's hard to do it with a transformer. You probably need a pi or T circuit. If you're doing something like an in-fed or an off-center fed where you're matching a very high impedance, then you can do it with the transformer. Either 49-to-1 or 64-to-1. Yeah.
You're starting.
Let's see. We did circuits at resonance, what the inductive reactance was, capacity, the resonant frequency. And then for the parallel circuit, the impedance is the reciprocal of the reciprocals, which is fun on a calculator. That's actually a case where it's probably easier to do it in admittance terms and then convert it back. And the Q we just did.